Hey everyone, welcome back to the second video in our series on classification. In this video, we'll build several k-nearest neighbors classifiers to fit some random data where we have a bunch of points. We know the x and the y location of the points, and we have those points belonging to three separate classes: a red class, a green class, and a blue class. This is going to be essentially the same data set as we saw in the first video, except we're going to make our classification problem a little bit harder by making the points and the groups not so separated. So we're going to have overlap this time between the red and the blue points. And so here's our training data. Essentially, the scenario is the same, though. In general, the red data points have large y coordinates. The blue data points live in the lower left quadrant of the feature space. And then the green data points are data points that have larger x coordinates but still small y coordinates. In that first video where we were introduced to classification schemes, we saw that the goal of a classification scheme or the goal of a classification problem is to draw fences to separate the groups in space. And that's what we'll do here. We're going to do this again using a classification scheme called k-nearest neighbors, where this is a voting classifier. I take a look at a point in space. I classify that point in space as belonging to the group where if I set, say, the nearest neighbors to 5, the 5 closest neighbors vote on what class that point in space should belong to, and the point ends up belonging to the class that gets the most votes. So it's kind of easy to wrap your head around what's going on here. The points vote, majority rules. So what we're going to do is we're going to build a set of probably 4 or 5, I think 4 classifiers. We're going to compute error metrics along the way, but we're not going to discuss them until the third video. So my goal here is just to show you what several different k-nearest neighbors classifiers look like and how varying the number of voting neighbors impacts the decision boundaries. Okay, so our first k-nearest neighbors classifier is going to classify points in space by asking the 15 closest training data points to that point in space what class they think the point in space should belong to, and the majority class, again, will win. What we're going to do is we're going to paint the space according to the classes. And so here what you're seeing is you're seeing the training data points plotted above a colored surface or a colored region. The colors in the background are the actual classifier. So the points at which the background region transitions from red to blue or red to green or blue to green, those are the decision boundaries. The region colored by red, any data point falling in that region would belong to the red class according to this classifier. And similar for the blue and green classes as well. So this is the model with 15 nearest neighbors. What we're going to do is vary that. We'll look at a similar model with 7, and then 3, and then 1 nearest neighbor classifier. Again, we're not going to talk about the error or performance metrics in this video. We'll wait until the third video to do that. So again, here's the k-nearest neighbors classifier with 15 nearest neighbors doing the voting. What we can do is we can plot now the unseen test data on top of that classifier, and we can see visually what the performance of the classifier was. So you can see in the red region, we got a few points right. So here's 2 red observations that were classified correctly. But here's a red observation in our test data set that we misclassified. We predicted it would be green when it was actually red. You can see kind of a cluster of reds over here that were misclassified as well. So again, our goal is to build a classification scheme or a classification model that will minimize the errors made on unseen test, safe, or future data. So let's take a look at what a k-nearest neighbors classifier looks like if we change k to 7. So here's that same training data, but now we're letting only the nearest 7 neighbors vote. Now, if you think about the power that each individual training observation has now, each individual training observation has become more powerful. Because for any region in space, a voting member now has 1/7 of the total determination, the total vote power. So each individual training observations counts as 1 vote out of a total of 7 rather than 1 vote out of a total of 15. So this gives more power to individual data points by lowering the number of voting neighbors. And what you can see is we get a more intricate decision boundary being made. So you can see the red region kind of protruding down here into the green region. The green region's been separated into a couple of pieces. You have a red island, another blue island. And so the decision boundary has become more curved, more flexible. Dropping the number of voters has increased the flexibility of the model. Remember, though, that risks overfitting. And so if we take a look at our test data, we see visually that, well, it looks like this model might be doing a little bit better than our first one, visually. But we'll come back to assessing the models using our performance metrics in the third video. Let's just quickly take a look at k-nearest neighbors with 3 nearest neighbors. I'm going to cruise through the performance metrics, and we'll talk about them in the third video. So again, you see that dropping the number of voting neighbors increases the power of each individual voting training observation. So for any region in space, we're looking at only the 3 nearest neighbors. Each individual training observation then that's a voting member for that region is 1 out of 3 total votes. So each individual training observations vote counts for a greater, it has greater determining factor. And so again, here's the training data plotted on top of the decision boundaries resulting from a k-nearest neighbors with 3 voting neighbors as our classifier. And you can see the decision boundary, again, is a pretty intricate, curved, pretty bendy boundary. And if we move down now to the most flexible k-nearest neighbors model, a k-nearest neighbors model where we have just 1 voting neighbor, we look at the single nearest neighbor, and then that single neighbor determines that the color of that region in space, or the group that region in space is assigned to. Then we get some really interesting behavior. But again, remember, increasing flexibility, yes, improves performance on the training data, but it doesn't necessarily mean that performance on the test data will be improved too. We need the performance metrics in order to be able to assess that. And that's what we'll look at in the third video, the final video of this series. So again, thanks for following me through with this second video. I hope at this point, a classification problem and a classification scheme are becoming a little bit more intuitive to you. Again, we're just trying to draw fences. I'll see you in the third video when we talk about assessing these models. Thanks, everyone.